Okay, so today what we're going to do is we're going to talk about population growth. So we've gone over relationships in ecology. We've gone over some strategies like reproductive strategies and maybe camouflage and mimicry, stuff like that. So today we're talking about population growth. Okay, so what we're going to do tomorrow we're gonna look at some math. We're going to be able to look at how ecologists might be able to figure out how big a population is, right? So we'll talk about that tomorrow. We'll look at it conceptually today, but tomorrow we'll do that. We'll talk about the math. So tomorrow we'll talk about things like how do you calculate population density? So what do you think population density is, Jerusha? What do you think it is? Yeah, but of one species, right? It's the amount of individuals in one species living in a particular area. So it's important because you'll see later on we'll talk about density dependent factors, and you might want to know how dense your population is to understand some of the issues that a population may face as it becomes really, really dense. Give me an example with humans. What would be an issue in a very highly dense human population that would be different in a population that was maybe had very low density? Like maybe out in the farm, for example, right? Maybe a population like living on farms where you don't come in contact with each other very often. How would how would it be different living in that kind of environment versus an environment where there are like thousands and thousands of people living in a very small area, like downtown Toronto? Like how would that be different? Like how would that affect ecology or anything? So what would density, why would you be interested in density of a population? Okay, I'll give you, there's a few things. Let's talk about one, because we did in the immune system. What about disease? Right. The density of a population will affect how easily disease might spread, right? So you would expect that in, very highly dense populations, the disease might spread more quickly. So, tomorrow we'll talk about the math of population density. Okay. So today we're going to look a little bit about, talk a little bit about population growth patterns. So, and again, tomorrow we'll model it mathematically. So today what we'll talk about is things that will affect growth patterns. So here I put up 6 on the board. So I'm going to ask you a question. You tell me if how it affects the growth rate. High birth rate. How would that affect the growth rate? What if I told you the birth rate is higher than the death rate? What would you tell me? Population will grow or get smaller? Grow, right? It's pretty obvious. So I think we kind of understand the impact of birth rate and death rate. Immigration and emigration. So which of these two terms would make a population increase in size? Yeah, immigration would make the population get bigger. Emigration means the population would lose individuals. So birth rate, death rate, immigration, emigration is pretty easy to understand. Tomorrow I'll show you a formula that uses those 4 things in calculating this, the change in population. That's pretty easy to understand. But there are 2 other terms up here that may be a little bit harder to understand, like age distribution. What does age distribution have anything to do with a population and maybe its ability to grow? So we have 3 population pyramids. Have you guys ever seen these in social science? No? You might have in other courses. You have a breakdown of 3 different populations by age. So how does Nigeria, now this information is at least 10 years old, so I don't know how different it would be today. It might be a little bit different. You have Nigeria on the left and Germany on the right and the US in the middle. Let's look at Nigeria versus Germany. How is it different? Where is the broadest part of the pyramid in Nigeria? The bottom. Now the bottom, if you look at the y-axis, it's the breakdown by age. So this is saying that most Nigerians, if you look at the biggest group, it would be young people, right? And as you work your way up, there's less and less individuals. If you look at Germany, the biggest group is actually where? Not in the bottom. Where is it? It's in the middle. Okay? So this looks like an actual pyramid. This kind of looks like almost, not wouldn't be like an hourglass, but like an oval, I guess, where the bulk of it is in the middle. Which of these two populations has a higher potential to grow? And why? Iris, which one? Which of these two populations has a higher potential to grow? Well, think about it in 10, 20 years, right? In 10, 20 years, you have a very narrow base of kids. In 10, 20 years, those kids will be what? They'll be adults. But will you have a lot of them or very little of them? Very little of them, right? So what about in Nigeria? You have a lot of kids. In 10, 20 years, those kids will be what? They'll be adults. And adults have babies. So the population on the left says that this population can grow pretty quickly because there's a lot of kids. And a lot of kids means you could potentially have a lot of adults. But here's the thing. Why is it that the population just narrows out like that? Why? Why do you think it does that? It tells you something about the standard of living in that country, right? Which country has a higher standard of living? Which country has a higher life expectancy? Which one? Think of it. Look, how many people get to old age in Germany, in Nigeria?
Thank you so much.
Is it a lot? No, very few, right? If you look at Germany, it's much broader. Okay? So the difference here is you can see that there's a much higher standard of living in Germany because more people get to old age. So the death rate is lower in Germany than it is in Nigeria, right? But in terms of potential, the Nigerian population has a higher potential for growth, but in actuality, there's obviously a much higher death rate too, as we go up the pyramid. The U.S. is kind of like in the middle, so you can see it still has a pretty broad base, which means it has good potential for growth. Not as much potential as Nigeria would, but the death rate would also be much lower in the U.S. than it would be in Nigeria. So you have a higher chance of getting to older age if you are a child. So the distribution of age does tell you something about the population. If you have a lot of young individuals, that population can explode on you because those young individuals will become adults, right? So an ecologist might want to know when he's looking at a population of animals to see, like, are there a lot of kids? Are there very few kids? If there are very few kids, that population could crash in the future, right? What about sex ratio? Why is that important? Why is it important to understand the number of females versus males in a population? Assuming that there are females and males, because not every population has females and males, right? But the ones that we are probably going to talk about are sexually reproducing, have females and males. Why would you want to know about the number of girls and boys in a population? How would that affect the ability to grow? What do you think? So imagine you have a population that has very few girls. Yeah. So maybe as an ecologist, you might call your friend Bob, who maybe he's living in an area where they have lots of girls of this species, and say, hey, Bob, can you bring over some females? Because this side of the world, we have very few individuals that are girls. And that's a problem because not enough females means what? Not enough babies, right? So the sex ratio is important. So the biotic potential is the ability for a population to grow. And we talked about, some factors that would affect the growth rate. But another potential is not what will actually happen, okay? Because there are things that will affect the actual population. For example, the biotic potential of a fruit fly is much higher than it is for an elephant. Because if you think about the birth rate of a fruit fly versus an elephant, what do you think? Way higher. But when we look at the death rate of a fruit fly, it is also much higher than an elephant, right? So the biotic potential is the ability of a population to grow, and we know that we just talked about there are certain factors that will affect the growth. Here's the thing. When conditions are ideal, all populations will grow this way. So what kind of growth is this? This is what? Exponential, right? Exponential. Now here's the thing. If this was the case for every population, then the world would be covered in organisms. You would not be able to move. You would always bump into some other organism. Why is this not the case? Why is this? So take for instance like Daphnia. Okay, so here's Daphnia. It's also known as a water flea. Okay, there's babies in the back. You notice this image has two babies. So assuming that every Daphnia has two babies, and they don't, they could have 20 babies, but let's keep it simple. Then 1 becomes 2, then 2 become 4, because they each have 2 babies each. And then you get this doubling effect. If you were to map that out, graph it, that would be exponential growth. So here's a picture of my living, no, just kidding. So exponential growth. Populations grow exponentially, they go out of control. Why don't we see that? What goes on? What happens to a population? Take a look at this picture. So you notice that the first part looks exponential, but then what happens? It levels off, right? Or maybe it even crashes. Why does it do that? Why does it level off or even crash? What causes it to stabilize? So imagine this is an aquatic system. Maybe you're monitoring the size of a particular fish. Maybe you'll notice this exponential growth, but eventually it levels off. What causes it to level off? Yeah, because as we talked about with the example with the lynx and the hare, right? That as populations grow, then there's going to be less food for them, less space, maybe less oxygen, maybe disease will spread more easily. So populations under ideal conditions can grow exponentially, but realistically there are always limiting factors. There are always things that will limit the size of a population. And there's something called a carrying capacity, which says basically, based on the amount of food, the amount of space, the amount of water, the amount of sunlight, this is pretty much the ideal size of a population. And we'll talk about that one tomorrow. We'll talk about the carrying capacity and how we can actually use it in our math to figure out the size of a population. Okay, so we're not going to talk about any math today. We will talk about that next. Hold on, wait. I'm just recording something. Okay. Alright, so here you see an example of a population grow, maybe reach stability and then crash. This could be, for example, well, actually not could be, it tells you what it is. In this case, this is like waste accumulation from a population, because if the population grows in size, each individual produces more waste, right? If you can't get rid of the waste, it just accumulates and then eventually will kill the population. This is, by the way, what happens, for example, when people make alcohol. The yeast is producing alcohol by converting the sugar into alcohol. The alcohol levels will rise, the yeast population will grow, but eventually what happens, the alcohol percentage becomes too high. So it becomes toxic to the yeast and ends up killing them, and then the yeast will crash. Okay, so let's talk about density-dependent factors then, okay? So these are factors that will limit the size of a population, and the effect of the factor depends on the density of the population. Because right now we're looking at things that will affect population growth, okay? So something like food. Food would be a density-dependent factor, because if I have a lot of individuals living in an area, then the availability of food will be affected by the density of the population. So for instance, I can imagine that if I have like a city, and I have thousands and thousands of people living in the city, and there's a food shortage, that's a problem, because there's so many people now, and there's not enough food. I can imagine that maybe if there's not enough food, but there's only a few people in the area, that might not be as big an issue, okay? Because when you look at a factor, if the density of the population affects the factor in any way, that would be considered a density-dependent factor. So like disease. Does the density of a population affect the ability of a disease to spread? Yes, it does. So then that will be considered a density-dependent factor. Food is a density-dependent factor. Would oxygen in an aquatic ecosystem be a density-dependent factor? What do you think? Yeah, because if there are more individuals in an area, each using up more oxygen, then there's going to be less oxygen in the system, right? What about predators? Is predators density dependent? Think back to your lynx and hare population cycling there. Does the number of hare in an area, density of hares, does that affect the predators in any way? Yeah, it does. It does. Because you'll get more predators over time. So density-dependent factors are things that, again, are dependent on the density, like the availability of food. You'll notice something. If you look at the pattern, a density-dependent factor will become a big problem when the population is high. So think of this as the effectiveness of the factor, okay, on the y-axis. So as we go up, the factor becomes more significant. So if this was like food, as the population increases, food becomes more of an issue, okay? As the population decreases, food becomes less of an issue. When you look at density-dependent factors, you'll notice that they do something to a population. As a population increases and food becomes harder to find, that was going back to the example that's a food shortage and you have hundreds of thousands of people, it's going to be, most people will not find any food, right? What will happen then to your population? It will crash. People will die. Individuals will die. When there's less individuals need less food. So then what could happen is the population could rebound. This is, for example, like with the lynx and the hare, right? When we have a high population of hare, there's not enough food for them. Population crashes. When there's a low population of hare, there's a lot of food for them. Population rebounds. What pattern do you see here? Where have you seen this pattern before? Think hormones. This is a blank feedback system. Come on, you've seen this before. Come on, girls, you've seen this. You saw it numerous times actually in this course. But just to show you one of the most recent times you saw it was right here. So if we go back to the presentation on the endocrine system, where have you seen that pattern? What's that pattern called? Yeah, it's called a negative feedback pattern. There's the one on sugar. That's calcium. And then there is the one on sugar, but for some reason, oh, right here. And then there's the one on sugar. Okay. So you can clearly see that it's the same pattern. It is a negative feedback pattern. Okay. So things that affect population growth and population size, there are two types. There's density-dependent factors that you can see, will generate a negative feedback system or response. Okay, so here's two other examples of negative feedback factors. So take a look at this graph. You have the number of seeds that a plant will produce on the y-axis, and you have the number of plants in an area. So what happens when we have more plants living in a particular area? Do they produce more seeds per individual, or do they produce less seeds per individual? What do you notice? When we have very few plants in an area, so as we go this way, there are less plants. They produce more or less seeds? More, right? When we have more plants, they produce why? Okay, we're going to think about that one. And if on this graph on the right, it's very similar thing. You have the density of females, so that's the number of birds living in an area, and you have the number of offspring. And you'll notice that when you have very few birds living in an area, they produce more offspring, and when there's more, they produce less. Why? What's going on? And this is an example of a density-dependent factor, obviously, right? Because what you're seeing is dependent on the density of the population. Why is this the case? So if you're a plant and you're living in an area where there's lots of other plants around you, is it harder or easier to get water? It's harder. Is it harder or easier to get nutrients? Harder. Is it harder or easier to get sun? Harder, right? So it becomes harder to get all of these things that allow you to grow and make energy and have babies. Because making babies requires energy and it requires nutrients. Same thing with the birds. If you're living in an area where there's lots of competition with other birds, it's going to be harder to find water, harder to find food, harder to find good nesting sites. So, in other words, harder to make energy, harder to get nutrients, harder to have babies. A density-independent factor would be something that has not, like the density of the population does not have any impact on the factor itself. In other words, if you think about like a hurricane, is the likelihood of a hurricane more or less depending on the size of the population? Or does the size of the population have anything to do with whether or not a hurricane is going to hit? It has nothing to do with a hurricane. Whether there are a few rabbits or a lot of rabbits in a forest, will that affect the chance of an earthquake happening? No. Or an asteroid hitting? No. So those are called density independent factors. But would the size of the population have any effect on how easy a disease will spread? Yes. That's a density dependent factor though. Okay? Alright. So we talked about population growth patterns. We talked about factors that will affect the population growth. We already talked about the survivorship curves and reproductive strategies. So I believe that is it. Tomorrow, because we talked about the population growth curves, tomorrow we'll do the math. Okay, guys? Tomorrow we'll talk about the math behind population growth models. All right? Ladies, that's it for today.